Yeah, I'm a software developer at Linum Labs. So I'm going to be presenting a tool that we're working on, sort of side project that we've recently open sourced. And I'll start off with a bit of a story. Let me just share my screen. Cool. Can you all see my screen, the presentation?
Yep, perfect.
Okay, oops. Okay. So last year, Ryan Noble and myself, he's on the call as well. We were heading off to the Status Hackathon, and we sort of left, or I left with a basic understanding of bonding curves and how they worked. And we were sitting at the airport terminal and started theorizing about what we were going to build at the hackathon. And we decided that somehow we wanted to integrate a bonding curve to represent reputation as a sort of curation market. And after that, we weren't sitting on the airplane together. So we went off our own ways and both went into separate rabbit holes. And when we arrived at the hackathon, I think this was day 2 of the event, we started integrating the bonding curve. And at about 3 a.m. that night, after a beer or two, decided that it would be a good idea to take this bonding curve and make it die-backed to properly represent reputation in the system we were building. And so we stood there with pen and paper trying to plot and discuss all these curves. And yeah, it was quite a challenge, especially with all of us frantically trying to get these integrations in. And we probably could have used MATLAB, but there was nothing specific for bonding curve design. We started seeing difficulty with visualizing the curve we wanted to use. And also some of the challenges we ran into were that we were trying to plot a linear bonding curve. I mean, initially we wanted some sort of, I don't know, sigmoid or something more complex, but as soon as you start doing integrals of second and higher order functions and solidity, it becomes quite complex. You can use things like numeric integration or approximations, but they either become expensive or inaccurate. And yeah, we also started, this ideally simple bonding curve that we wanted to implement was quite complex as well because of floating point operations and solidity, and sort of having to wrap our heads around that a bit. And then also, we started talking about how people interact with bonding curves and, some of the game theory of the curve design that we were wanting to implement. And all these things were quite difficult to just draw up and talk about. And often bonding curve design involves multiple members of the team. So we needed some sort of, if you wanted a tool to help design bonding curves, you need some sort of something that helps you with collaboration. Maybe you've got operations, people involved in, I don't know, finance in your project. It's not only the developers that need to be interacting with the designs. And yeah, bonding curves are quite a new idea. As developers, we like to think we know what's going on, but you need to, there's a lot of limitations as soon as you start implementing it on smart contracts. And there's also a lot of new designs coming out, like multi-collateral bonding curves, bonding curves with stable collateral like DAI, multiple stage bonding curves with, sort of dynamic changes between the bonding curves. And there's no real way to onboard people into understanding how all these features work and interact with each other and the unique benefits you can get from it. Okay, so let me jump across to the actual app just to demo it a bit. Okay, so yeah, we've got a open repo that you guys can look at in your own time. But the app is quite basic at the moment, but there was quite a lot of complexities in the back end that I'll talk about now. So what we've tried to do is make this, well, when I say backend, I mean JavaScript, because what we're trying to do is make this purely front end to keep it simple, make sure that people can collaborate on it easily, add different examples, different documentation about bonding curves. We don't want people having to fiddle with the backend. So basically what happens is you can either enter in your bonding function as a function of the tokens, the price on the bonding curve. So we've got a few examples here: linear, quadratic, square root, sigmoid. So sigmoid, and then you can choose the token supply. It slows it down a little bit with the more tokens you have, so the scaling here for that sort of token supply doesn't look correct, but if we scale it down again to say 5,000, you can, as you're playing with these curve designs, you can edit the parameters of your curve to make it look and behave how you'd like. So here we've got a basic sigmoid curve, and at the moment, the idea is that as you go through all these different plots, you'll be able to get a basic understanding of what these plots actually are. So here we've got a basic description of bonding curves. Underneath, we could have the equation, or for sort of collateral and implied valuation, once again, you can have a description of what that means in the equation. We've added a few curves here that we think are useful when you're designing bonding curves, but the idea with it being open source is that people could add on additional functionality. So jumping back to the presentation. Okay, so the basic idea is that we want to experiment with design of bonding curves. We want to be able to enter in any reasonable bonding function. And a next step that we want to include is something like parameter controls, so that you can control parameters within a set reasonable limit and see how that changes the behavior of the bonding curve. So you could maybe choose unstable versus stable collateral and have some sort of historical plot of how that would affect your bonding curve. Obviously not the actual curve, but the sort of simulated trading. We want to be able to sort of visualize multi-stage, multi-collateral bonding curves, and also a current branch feature that we're working on is simulating trading interactions. So having different users of the curve and having them buy and sell and see how the value that they've got in the curve changes over time. And also we can use it as a teaching tool. So, have guided constraints and examples. The website, I think having terminology explained will help a lot as well, along with the visual sort of learning experience. And also, when you sharing and collaborating on bonding curve design, whether that's, people saying, oh, look at this new curve that we've created, or this new feature, you could, share it on Twitter or send a direct link to people within your team. So as I mentioned, one of the challenges we came about was that as soon as you start having any more than about 10,000 data points, when you're processing that on the front end on a sort of run-of-the-mill laptop, it becomes quite heavy. So we've got some JavaScript web workers in there to help ease the load, and also a few sort of mathematical approximations like decimation and downsampling, and then interpolating between the points. And for better sort of memory management, we've got memorization as well. Cool. So roadmap and future features. We need trading simulator, which is a work in progress. Historical plotting of trades. So that'll take a bit of work. I have to do some sort of, yeah, that'll take quite a lot more work. Curve parameter controls, sliders, and as mentioned previously, getting some sort of bonding curve theory and terminology in there, which some of you more experienced guys can help us with. Cool. So yeah, we've got the website up on Netlify. This was just kind of it's a side project for us, so we just want to ease the load and not host it ourselves. It's deployed automatically off the master branch of Bonding Curve Playground. And myself and Michael and the rest of the team were the initial contributors on the project. That's it.
Awesome. Very cool. Thanks so much, Ben. Do you guys have any questions on Ben's presentation? You're welcome to drop them into the chat, or you can also just unmute yourself. Some good feedback then in the chat. Cool. Otherwise, I can also carry forward question time through to the open floor discussion at the end if you guys would like to chat about it a little bit further then. And in the meantime, I'm going to ask Billy if you would like to start your presentation now.
Sure.
Cool.
Hi, everybody.
Yeah, Billy will be presenting on batch bonding curves to combat front running and adjustable collateral. Cool.
Yeah, so let me share my screen. Is that visible to everybody?
Yep, got it.
Cool. I got the cheesiest theme I could find from the Google presentation shop. Hope you all enjoy it. All right, is that up?
Yep, we got it.
Cool.
Perfect.
So like Devin said, I'm going to be talking about batch bonding curves. A little about me. I'm involved in a bunch of different projects. The one closest to my heart is Clover's network, which is being built by Bin Studio, which is that second link. I've also built the Meme Lords app, which has yet to be pushed to mainnet. ENS Nifty. I work for Cosmos Network, and I also do research for Gnosis. Today, I'm going to be giving you a little background on the research, where this work came from, a little bit of talk on front running in general. I've kind of come up with 3 batch bonding curve proposals that are meant to combat front running. So I'll go through each of those. The first one I'm calling batch to ordered, second match and fill, the third is a common clearing price. I've got some documentation for all of this work. There's a GitHub repo, there's an observable with a lot of nice sort of graphs and numbers you can play around with. As Devin mentioned, I'm also going to talk about adjustable collateral a little bit. That's a little bit separate of a topic, so I just put it as a bonus at the end. And then, yeah, questions, discussions, which I think should be able to lead into the open floor stuff. I'm not sure if I can't see the messages while I'm talking, so I'm not sure what the best way to respond to those are. But so I guess if somebody has something to say, feel free to speak up, because I won't be able to see the messages. So background research. This actually all began because of some work that I've been doing for Gnosis regarding continuous organizations. And if you're not familiar with that concept, there's a lot of writing about it, a lot of different ones, especially around apiary from Aragon with Luke Duncan being worked on by Pando and 4ire, others, as well as continuous organization from Thibaut Favre. DXDAO is sort of the topic that I've been working on more specifically with Gnosis. It's involved with DAO Stack, also Jeff Emmett and others from Giveth have all been sort of working around this topic. But the basic idea behind a continuous organization is that the shares that are bought and sold are done so with a bonding curve. The collateral that's locked up in that process, part of it is used for working collateral, working capital. for that organization. And there's a couple different ways that can be done. And so a lot of the work we've been doing is sort of trying to figure out all the different options and evaluate each of them to make judgments when building as apiary or Sea Org or whatever they are. The other part that is mostly present in these situations is that token holders would receive some dividends, or they'd receive some ability within the organization, whether it was special voting rights or just sort of the sponsorship badge, whatever it is, there's sort of like a reason that you would hold these tokens to begin with. Of course, whenever you have on-chain tokens going out, all trading becomes insider trading. And so you have this problem, like when dividends are going to be paid, what amount they're going to be paid, all of this is on chain. And so it kind of becomes public knowledge from the beginning. And so you have the options for insider trading is sort of always on the table. And that is basically a form of front running. Front running is always possible whenever there's some guaranteed price movement. And so you can imagine with the traditional exchange system, there's a buy order coming in. Someone would want to sandwich that order with their own buy and sell. There's a guaranteed profit there because they know that the following buy order will push the price up. So they enter right before it. Once the price is up from that guaranteed one, they can sell again. So with zero risk, they're able to make a profit just by sandwiching your order. Similarly, but less spoken about, is that you can do this with sell orders, which is that when you see a sell order coming in, you can similarly sell right before and then buy right afterwards. This means that you're able to basically increase your current holdings without any sort of risk. And you can see a sort of similar parallel with the idea of dividends being paid out, that as soon as you see a dividends payment coming in, whether that's an injection of collateral into that collateral pool, or whether it's minting a bunch of new tokens that are going to be distributed to current token holders, you can kind of watch for those kinds of transactions and do a similar sandwich where you're either buying before it and selling right after for the dividends, or alternatively, if working capital is being taken out, this may change the current price. And so you can also increase your current holdings by selling immediately before and buying immediately afterwards because you have this guaranteed price movement. This is a huge problem, and it has been occurring in the wild. I strongly recommend, if you haven't already, to check out Phil Dine's presentation at DevCon, Smart Contract Security, Incentives Beyond the Launch. He was involved with this publication about front running on Bancor, and they also did their own experiments on front running with Ether Delta, and they reported being able to make $4,500 in one day in August 2017, and that was on Ether Delta alone. So you can imagine all the sort of developments that have taken place since August 2017 with on-chain exchanges, the scale that's increased. This diagram on the right sort of shows the vertical line is when they first published the findings of the ability to front run and sort of the techniques for doing so. And then they started tracking what they're calling programmatic arbitrage transactions, which are transactions that you can kind of identify were made by a bot based on some sort of logic, which would be the same logic utilized for a front-running event. And after the article, the number of these types of transactions just sort of skyrocketed. That's the noise to the right of the line. And so this is a very real problem and a very real threat. They estimated that 30% of all blocks contain some kind of programmatic arbitrage transaction. There's been some research about one solution that is called Submarine Transactions, which involves a pretty complicated commit reveal scheme with an unknown contract. It's not a great user experience. There are a couple of prevention techniques put in place on, say, Bancor or on Uniswap, who similarly suffer from this problem. Bancor puts a max gas so that nobody's supposed to be able to accelerate the gas prices above each other, but that doesn't prevent actual miners from ordering blocks or front-running the transactions. There's also the minimum return, which means that if somebody gets in front of you and you don't get back your expected value, your transaction will fail. But this is a pretty terrible user experience if you have to overestimate all your transactions and expect a loss just to get the transaction to go through. Uniswap uses a timeout. So they say this transaction will fail unless it's executed within the next, and then you can set 30 seconds or whatever, however many time period you want, so that a miner wouldn't be able to hold on to your transactions and execute them at a later date when it's more convenient. So these are all sort of some mitigations that are out there, but they all have their own problems. So enter batch bonding curves. This was inspired by the Dutch X design, which is an on-chain exchange that's been designed by the Gnosis X, by Gnosis, and will be managed by the DX DAO, which is a really interesting project that is forming over the next couple of months. So if you're interested in being part of the DX DAO, who will be in charge of the Dutch X, you should look that up. But they have a 6-hour cycle, roughly 6-hour cycle of buy and sell orders. It's just a continuous Dutch auction. And this sort of defeats the ability to front run any sort of buy or sell orders. The slogan is something like good trades take time, which I think is pretty great. But the logic of sort of grouping a bunch of transactions together and finding a clearing price after the fact based on when they entered and what the supply and demand for that period is very much applicable to bonding curves. So we use that as a starting point, and all of the different designs sort of have similar attributes, which is that over some period of blocks, whether it just be over 1 block or over 10 blocks, you would collect all of the buy orders and all of the sell orders. And then after that 1 block, 10 block, whatever, however many blocks clear, you would come and trigger a transaction to collect however many tokens you bought or however much collateral you made when selling tokens. This collection transaction is not a great user experience, but there's no reason that it couldn't be executed by any public individual. It doesn't have any, sensitive permissions on it. So you could potentially set up a bot who would, distribute the purchase or sell results afterwards. You could also potentially build in a reward fee so that anybody would, find some small reward to do that public good of sort of making sure that you received your buy or your sell a couple blocks after you made it. So that would, I think, do a great deal to mitigate the user experience problem of not having instant instant returns from your purchases. And the 3 that I've sort of outlined so far, I was mentioning before, calling them batched and ordered, match and fill, and common clearing price. So batched and ordered is kind of the least sophisticated. You decide basically beforehand that there's going to be one group of participants who are going to be rewarded over the others. And the reason that is because as you collect all of the buy orders and as you collect all the sell orders, the order that you execute them is going to make a big difference to what each price would be or what the accumulative price would be. And so you have to, if you're going to use, the typical bonding curve purchase return mechanism, which, as we all know, sort of changes depending on how many tokens you're trying to buy or how many tokens you're trying to sell. Especially because when you are selling, you're typically selling a number of tokens. And when you're buying, you're typically spending some amount of collateral. And so the number of tokens you get as a result of that collateral will depend on the current price, and the amount of collateral you'll get on that sell order of tokens will also depend on the current price. And the sells will change the price in one direction and the buys would change the price in the other. All 3 of these models, when actually calculating this, it's much easier, and there's no reason not to just group all of the buys together and all of the sells together as basically one big buy order and one big sell order. And so this is kind of a commonality as well between all 3. And in this first scenario, the batched and orders, you just decide arbitrarily, okay, we're going to execute all of the buys first, and then we're going to execute all of the sells first. Afterwards, we're going to take the results of each of those, and then we're going to check how much money did you put in. Okay, you put in 1/3 of the total, you get 1/3 of the result. If you were to execute all of the buys first, this would be a reward for the sellers because after the buys take place, the general price will move up. And then if the sellers were to execute their orders, they would benefit from this new high price because, of course, sellers want to sell high. Alternatively, if you executed the sells first, the price would move down from the initial point, and the buyers would benefit from this because, of course, buyers want to buy low. You could also say that this is a feature, not a bug. In a lot of situations, you might say, I would rather reward the buyers over the sellers for my bonding curve token because the buyers are contributing to the ecosystem, they're adding money in, whereas the sellers are exiting. They are losing confidence or moving away. Similar ideas about taxing the buys and not taxing the sells or adding fees to those. That same sort of logic would apply. Also, it's interesting to note that if you execute the same amount of buys and sells in different orders, the scenario that rewards the buyers, if you execute it that way, the final clearing price will be higher than if you execute and you reward the sellers. That final clearing price will be, in general, lower. So you also, you could say it's like a benefit to your ecosystem that you are executing the sells first and rewarding the buyers because you like buyers, but also you want the general price of your token to continually move upwards. So those are two signals that would, two features that would come with this first technique, the batch and ordered. It's also arguably the easiest to execute because, again, you're just executing one normal buy order and one normal sell order, which most bonding curve contracts are set up to do already. There's a little bit of tedium in keeping track of the proportion of the buys and sells for each group, but that's relatively painless as well. So the second one, oh, this is my diagram for all those topics I was just speaking about. The second one, which is mislabeled 1 here, is the match and fill. I have to thank Martin Kopelman for this design. This is where, as we all know, there is a current price for any like batched, any bonding curve token scenario. This current price is misleading because as soon as you start executing on it, that price will move. And so we generally try not to trust the like exact current price because it's not as helpful as knowing what the applied price would be when you actually execute on an order. But we do have, this idea of a current price. And so if we have a batch of buys and we have a batch of sells, why don't we try to match them at that current price and execute as many as possible at that current price? If that's done, you will always have one side who's a little bit bigger than the other. I mean, it's also possible that they're just the exact right proportion to execute at that current price, but of course, chances are low for that. In that scenario, you're done. Without that scenario, you're left with a little bit of a remainder of sells or a little bit of a remainder of buys. In that situation, you would have finished half your job. You would have cleared, say, all of the sells, and all you have now are a couple buys that are left over. Sells are done. They could basically, withdraw at that point. What you do with the remaining buys is you would execute that like a normal bonding curve purchase, and then take the average of that bonding curve purchase with that match order buy and combine those and allow all the buyers to withdraw at the same price. So in that scenario, you've got all of these buys, which are getting executed at one price, and all these sells, which are getting executed at another price. Similar to the first scenario, except for these prices would be much closer to each other. And the difference between them, one is that exact current price, and the other one is either above a little bit or below that exact current price. And that's because there was more buyers or more sellers, which in a way intuitively makes sense that that price should be larger or smaller for them because they had more interest in the other group. There were more of them coming in or more of them trying to get out at the same moment. And so the current price should maybe move in that direction, which is an actual market movement. The common clearing price, also mislabeled as 1, but meant to be number 3. So this is when you would find a uniform buying price for all the buys and all the sells. This gets into some kind of hairy math. you often get multiple results. Some of them are imaginary numbers. I've been using Wolfram Alpha, as well as I think it's called NumPy, the Python library for symbolic math, and getting a lot of help from Tom Malter from Gnosis, who I have to shout out to. This is kind of the goal, like I said before. If you could imagine a batch transaction taking place, you would collect all of the buys and all the sells, and in a way you would want to find a common price for all of them based on the combo of all that interest. And so finding that method, I guess I can walk through a little bit. So the goal of that is that you want to find some common P, right? So that while you're selling X tokens, you're subtracting those tokens, it'll result in the removal of X, that number of tokens, times price, that universal price. And that'll result in some amount of collateral. So that's the selling part. On the other side is the buying, which is spending some amount C collateral, which means that you're adding collateral. It's going to result in the addition of some tokens, which will be the amount of collateral divided by that universal price. So if you use those, you can think about that the total change of tokens and the total change of collateral, the delta X and the delta C. In the instance of the total change of tokens, you'd have that negative X, which are all the selling people selling them. But you'd also have this addition of new tokens, which is C, that collateral, divided by P, that price. Alternatively, the delta collateral would be the new collateral, which was added from those buys, as well as the negative tokens times price, which is the collateral that's been removed by those sells. So if you think of delta X and delta C as being these equations based on this universal price, you can put it back into a integral of the slope formula. So here, you can see we have a purchase from some starting supply to a supply plus K, which would be, the new tokens that came in. We're talking about slope like mx to the n. And we have that integrated, you might recognize this. I think actually, not these ones, but some of these might have been borrowed from Slava's last article, which is great if you haven't seen it already. So you can substitute this, these delta C and delta K into this integral, and you're actually able to get a formula which reveals this universal price. I'm calling it underscore price here. The problem is that this category of formula doesn't really solve very easily for P. And so you end up getting a bunch of nasty numbers. Usually you get one number which would result in like a negative balance on the contract. You get one number which would result in no change at all from the beginning. And then you get one number which makes intuitive sense and is actually very close to the number given from the previous example. And so you have to do this sort of weird process of elimination to see which is the right price. Also, this degree of math isn't really possible on the Ethereum virtual machine. So you're stuck in this weird thing that there is an answer there, but it's not easy to find. But there's a solution to that. Because this solution is hard to find, we don't want to actually calculate it on the EVM, but it is easy to verify. And so taking a page out of Gnosis's book once again, they're working on this project called Diffusion, which is another version of the Dutch X that will calculate clearing prices based on many different token pairs all at the same time. However, this level of calculation is also really difficult. They're using ZK snarks for it, but they're also doing a sort of optimistic verification system, a little bit like TrueBit. And basically the idea behind it is that if you provide an answer, that answer can be like confirmed on chain, or at least that answer can be challenged, in which then it needs to go to that verification process. And so the way that we can easily verify it is that we can execute orders based on that price. And then we can look, okay, so we executed all these buys and all these sells at this universal price. Now let's look at the amount of collateral that's in the contract, and let's look at the number of tokens that exist. And let's make sure that those numbers still hold up in the context of our slope. So as long as those two numbers still equal a scenario that our slope hasn't changed, that means that that price was correct. If you used an incorrect price, you would have like a little bit too much collateral or a little bit too many tokens, which would actually result in a change of your slope. Maybe it would increase the severity of the slope, or maybe it would change the polynomial of it slightly. And so confirming those are actually pretty simple. I have the math to sort of show how that takes place inside the documentation that I'm going to pull up right in a second. But that's a really kind of nice and elegant way to use this ideal scenario that there's just a universal clearing price for both buys and sells. And I'd also really be curious your all's opinions after this, what you think intuitively feels more just, because while I was spending more and more time trying to figure out a way to get this universal price, because it seemed like the holy grail, as soon as I found it, it made me feel like actually maybe the buy and the sell shouldn't be cleared at the same price. In a way, the second scenario where if there's more buyers, you know, that price should reflect that, somehow feels like a little bit more accurate, but I'd be really curious what your all's opinion is about that exactly. So there's a GitHub repository with implementations of the first two on my GitHub at OKWithMe/batch bonding curves. There's a QR code if you want to go there directly. There's also this observable document that I mentioned, which is kind of like a Jupyter notebook. It has sort of working functions and working code built into some markdown. It's also completely editable. So like, I think I used a scenario with a curve of like a squared polynomial and some slope. Like if you just wanted to adjust that, the whole document would update with your new parameters. So that's a really, really great tool. I will be publishing these as soon as I add the universal implementation to them. So I hope that is useful, and that when it's completely live, but feel free to check it out right now in the almost finished sort of work in progress state that they both are. So this is the bonus about adjustable bonding curves. How are we doing on time? Am I okay?
We're still good on time. So the call, we could, I don't know, how much do you still have left to go, Billy? Otherwise, it's also, if you guys would like, you can carry on. The call officially only ends in 15 minutes, so you're welcome to keep going.
Sure. I don't know. I mean, I just wrote an article about all this stuff. I don't know if it's, if we should go over all of it, or if you guys have already seen some of it, but it's basically just saying, again, sort of my argument for why I prefer the Bancor implementation of a bonding curve over integrating a slope. I think it's important to discuss them with the slope formula because that's intuitively understandable. These are the sort of ways that we talk about slope and graphs that we're familiar with. But it's really simple to implement using this, the Bancor style where you have a connector weight or a collateral ratio, and you can still represent that as a slope formula. As you can see, this is what I thought those links were from earlier from Slava's last article, that in the polynomial and this slope formula is the same as 1 over r minus 1, r being the connector weight, a reserve ratio. And the m slope is just the balance times that polynomial over the token supply to that polynomial plus 1. So it's really easy to swap between a Bancor formula and a slope formula. I'd say if you're workshopping a curve, you should talk about it in these terms. But when you actually program it, I really recommend you do it this. And the reason is because you have adjustable token supply, adjustable collateral pool, and adjustable connector weight, or this reserve ratio. Whereas with a slope, if you were to say all of a sudden take a bunch of the collateral out and everyone sold all their tokens, there would not be enough collateral to go around. Whereas if you took a bunch of collateral out of this one, the only thing that would happen is just the severity of that pricing mechanism would self-adjust. So everyone would get money out. It's sort of like a self-healing thing, which is, I think, really, really interesting. The other part of it is that, your adjustments become design decisions. Like, are you going to take some of your collateral out for working capital? Are you going to mint some new tokens that didn't have collateral go in that process as like a inflation? If so, it's a lot easier to adjust your system if you have control of those parameters. You also have this question about like, okay, say I want to take some of the collateral out, but I don't want the current price to drop. You can swap out price dropping for the level of volatility. You can change basically the polynomial on that slope formula. And here's the sort of diagram talking about exactly that scenario. Say you begin with this scenario in the top right. You've got a connector weight of 0.5, which means it's a linear slope. It would be something like mx. You've got a balance of 100 collateral and you've got 200 tokens. That means that the current price is 1. So this is kind of a rough estimate of what that curve looks like. Say you want to take some of this collateral out. You want to lower the balance from 100 to 10 in each of these scenarios. In this scenario, you want to keep connector weight the same because you really like having a linear slope function. You think that that level of volatility is conducive to your community. If all you do is lower the balance, the pool balance for your working capital, your price will lower, as you can see here. You now have 10 as a numerator. And so your price now becomes 1 over 10 instead of 1. And in the diagram, you can see that price is much lower. However, the category of curve being linear has not changed. Alternatively, you think price is a really important notion and you don't want your users to feel like they just got robbed. You might adjust the connector weight along with adjusting the collateral balance. So here you also lower the balance to 10, but you lower your connector weight by a degree of 10. So that your current price remains stable. It's still at a price of 1, but of course there's way less collateral in here, and the way that was worked out was by adjusting the connector weight. So now you have this very kind of extreme exponential curve. So there's going to be maybe more volatility or something like that, but you haven't sacrificed the current price. So these become design decisions, which are much easier to implement in a working and evolving bonding curve than having to adjust the entire price formula. So that's all of it on the adjustable collateral part. You can find me, okay with me is my username on most things, or Billy Rennekamp, email studio@bin. And with that, I would love to open up the floor.
Amazing. Thank you so much, Billy. There was one question that came up actually just as you were starting from Simon asking when Meme Laws is going to mainnet.
It's a really good question. I mean, it's an open source project, and the reason it hasn't is because everyone involved in it is just bogged down with a million things at the same time. I think probably everyone's familiar with this idea of just being so excited about so many different things at the same time. It's hard to dedicate time in one direction at any given moment. But it is an open source project, and if you're interested in supporting that, like, I implore you to reach out to me, and I would really love that.
Thanks, Billy. Do you mind dropping also your contact details into the working doc maybe after the call as well? And to everyone asking, this call will be made available online as well with the presentation. So. There's another question from Ben that says, when batching, could you buy some of the average of the collateral that would be traded along the bonding curve?
So, yeah, he actually answered that shortly after. So.
Oh, okay.
And sorry, I don't understand the question, but did you say, Benjamin, that I did answer that?
You did, yeah.
Okay, cool. If you look through that document also that I gave through the observable, you'll see that I also outlined the like non-viable solutions, which have some of the more sort of like, well, what if you just had an average of that or an average of that? But a lot of the averages stop making sense because they're not weighted. So I started walking down sort of the weighted average path, but kind of felt like that wasn't going, so I switched off of that.
Billy, can you explain maybe how you would envision the batch design to kind of mitigate the mass exit issue and kind of give everyone a uniform exit price, which I think is really interesting if there was to be like like a bank run. Totally.
I forgot. Thanks for bringing that up. It's an actual huge feature of this whole system. There's always been this sort of debate about mass exits on a bonding curve that, you know, the last person out's not going to get any money, even if they all sort of tried to leave at the exact same moment. And with a system like this, if everyone leaves at the same time, you have to sort of consider what that span actually is. If you're using a batch bonding curve that's only doing one block at a time, it's probably a little bit harder to get everyone to exit all at the same moment. But if they're larger spans, or if there's some form of coordination, or maybe even that span could be extended for under certain situations, then everyone who sort of is in that one span of blocks, all making a sell at the same time, they will all be able to make that sell at the same price as each other. So there's none of this, I got in before them, or I got out before them. I'm boosting my gas prices to make sure that my transaction gets in front of them. No block stuffing. It's all that everyone would receive the same exit price. I'm getting a call. Does that speak to that, Paul, or was there other?
Yeah, absolutely. That answers it. Yeah, I think that's a super cool feature because it mitigates one big risk factor.
Absolutely.
So with regards to the adjustable bonding curve, is there a working example? Has this been let free on chain yet, or?
I mean, on Clover's network, all of the parameters are adjustable by an owner account. That's one way you could handle it. You could also, it depends on how you reference your collateral pool. It's probably a good idea to keep collateral pool as its own parameter and just let it like match the amount of, say, ether or whatever is actually being used as collateral. But if you didn't want to do that and you actually wanted to check the literal balance of collateral, then anybody could, increase collateral without minting new tokens. And in that way sort of have an impact on the overall price. That's a mechanism being used on Clover's network, where every time sort of there's like an ecosystem activity, if somebody like were to buy something within the project, the profits of that purchase just go straight into the collateral pool and make every other sort of token holder a little bit richer. Very quiet in here.
Are there any other questions or thoughts from anyone else? Maybe any comments on the presentation?
Does anybody want to speak to the question I had about what feels intuitively more correct, that there should be the same price for the buy and sells, or that whichever group is the larger constituent should have maybe a more severe price?
I was also wondering with that question of yours, maybe as long as you made the buyers and sellers aware of the mechanism you were using, that's, you're not forced to do that. If people look at the contracts, they can see it, but I would say give the buyers benefit.
I think I agree with your sentiment too on that, Billy, that buyers, people who are contributing to the ecosystem should receive the preferential treatment rather than the people withdrawing.
Right, yeah, that's correct. The decision in the implementation number 1. I can't remember my own names. What was that one called? Regardless, I'll trademark those names and we can refer to them easily in the future.
Yeah.
But yeah, I mean, I think that's totally a feature probably a lot of situations would call for. Maybe for like an actual on-chain exchange, it's less, where it's just about providing liquidity or something like that, and then you want it to be maybe as fair of a price as possible. But when it's like these sort of like project-specific funding mechanism, it seems very much you'd want to reward the buyers.
Only concern I would have there is if you're expecting your newer community members to eventually want to exit, they may be less likely to join on the margin if they knew they would get a poorer price on the back end.
True.
I suppose that's also kind of discouraging the speculative behavior that could be dangerous to these kinds of systems as well.
True. I'm also curious, like what number of transactions could you actually expect in any given batch? I mean, most of this is about mitigating front-running transactions in which it's not a coincidence that they're going in at the exact same time, but there's no longer a benefit to being right in front of or right behind somebody. is it actually that you are most likely going to be the only one in any, given span of blocks? Because like, what is the actual, I mean, we're looking at projects today that don't have massive transaction throughput, but, it's like, what it mostly does is remove the threat of front running, and you kind of end up by yourself as a result, maybe.
I would think it actually increases the incentive for, I can't figure out which side yet, but increases the incentive for one side to try to join the same block as somebody else.
Yeah, I mean, this actually sort of, this question of like watching the mempool and also watching the current blocks of seeing like, okay, there's like this many buys right now. Oh, there's this many sells. Like, oh, I could actually get a really good price if I go in right now. I won't get the bonding curve price. I'll get, whether it's like, I'll get the match price or something like that, which, I would much rather have because there's no slippage. So you have sort of this whole different mentality of trading as well. I mean, the middle, the second version, matched and bonding, in a way, it's like a real-time matching service, and then the scraps left over sort of go as a fallback into the bonding curve. And I think something about that is kind of nice, actually. Has more similarities to like a traditional matching buy and sell order trading scenario.
Maybe a last question on something that you've raised once or twice, is that a lot of the math around this isn't suitable for Solidity/EVM, which is something just general that we've noticed as well with like trying to code functions or like more complex functions into Solidity, and still having them run in an efficient way. Just what are your thoughts around implementing this on an on-chain environment if the EVM currently isn't suitable?
So the first two scenarios are totally suitable for the EVM. That's no problem at all. Super easy. Those are done. Those are in the GitHub repo I mentioned. The third scenario is not implemented, but should be trivial as long as you do this verification method. Because like I said, the verification is actually pretty simple math. And as long as you're making that initial calculation off-chain, say you had a bot that was running NumPy or something like that, it could trigger the clearing price. That clearing price is rather trivially confirmed, and then people are able to withdraw their transaction amounts based on that off-chain computation. So all of those things are totally possible with the EVM. On the related topic, I am learning Go right now and was playing with the Cosmos SDK, and it was so nice to like think about building bonding curves with like a real programming language and just sort of like having application specific abilities in that scenario. So those are things coming up, which if anybody's interested in really going deep on like a very complicated mechanism and not having to worry about the EVM, I implore you to check that out. It's a really fun developer kit.
One other potential area for more research anyway, I was speaking with Michael Zargam at Block Science, and we were talking about this issue of floating point in Solidity, and he kind of brought up the fact that there are other disciplines that deal with converting continuous functions into discrete time blocks, like in robotics. And there are a couple of different ways. I mean, for different use cases, it changes a little bit, but things like Taylor series approximations, numerical quadrature was another kind of method, and point differentials. I haven't looked into them too much, but they are potential areas of research that those continuous functions can be modeled in discrete segments for blockchains.
Yeah, this stuff is really exciting. I'm excited to see the upcoming results of the usage in the bonding curve scenarios.
I'll put those terms in the note just in case anybody didn't catch them.
think a lot of us are going to have sleepless nights tonight.
Thanks so much, Billy. We've reached time now, so I just want to say thank you so much to everyone for joining, and thank you as well to Ben and Billy for presenting. There are still 2 speaker slots available for next month. If you guys as well have any suggestions for changing up how we run these events, please also just drop the comments in the chat or reach out to me. If you do want to present, drop me an email. I think my email is in the calendar invite. Yeah, thanks again, guys. See you next month.
Thanks, everybody.
Thanks, Kevin. Bye, guys.
Cheers, everyone.
Thanks, all.
Bye. Cheers.
Cheers, guys.
Mm.